Okay, and I'm going to start. Let me just put a spotlight on both the moderators, and we can go from there. And I'm going to start the webinar in 5, 4, 3, 2, 1.
Okay, we can start. Hi, everyone. Welcome to the 5th webinar of the WCRP Explaining and Predicting Earth System Change as a Lighthouse activity webinar series. My name is Annalisa Kerki, and I work at the Institute of the Atmospheric Sciences and Climate at the National Research Council of Italy. And I will be one of the moderators today. Before we start the webinar, I would like to remind and advertise the event that is going to happen this October, the Open Science Conference in Kigali. And so here the slide with the details of the conference, and I just want to emphasize that the early bird registration has an extended deadline, so you have time up to the 25th of July to register to the conference that we expect will be a very, very interesting moment of interaction and exchange for our climate science. And now we go to the webinar series. So this webinar series, as I mentioned, is part of the WCRP Lighthouse activity on explaining and predicting Earth system change. And posted on the chat, there should be a link where you can find more details if you want about this Lighthouse activity. The today focus is on Earth Energy Imbalance. That is also quite timely and also linked in context with global warming trends that we are experiencing. And now I pass to the other moderators today, Lijing Chang. Thank you.
Okay, and a very warm welcome from my side. I'm Li Jinchen from Institute of Atmospheric Physics, Chinese Academy of Sciences, Beijing, China. Before I introduce our first speaker, I'd like to provide an overview of today's events and the modes for interactions. So we have three speakers today. Three speakers will present before the Q&A session. However, during the talks, please feel free to pose questions and indicate to whom your question is directed to using the Q&A feature at the bottom of the Zoom window. And everyone can upvote the questions posted here. So please reserve the chat function for technical issues related to the webinar and use the Q&A session for questions. And we will then get to these questions in the discussion session following the presentations. So we also have a number of experts in the audience, so we want to encourage a lot of interactions during the discussion session. So for the presenters, we will give you a warning when 5 minutes are left and when 1 minute is left for you to wrap up. And now it's my pleasure to introduce our first speaker, Dr. Corinna von Schuckmann. Corinna is a physical oceanographer at Mercator Ocean, France, with a particular focus on the role of ocean in the Earth's climate system. She is lead author of Copernicus Marine Ocean Reporting Framework, lead author of IPCC Special Report Ocean and Cryosphere, AR6, and the second, the IOC Global Ocean Science Report, and also contributes to WMO State of Climate, and one member of European Academy of Sciences and various international science panels. So thank you, Corinna, for being here, and the floor is yours now. So can you share the screen and start? Thank you.
Thank you very much for the invitation and the introduction into this topic and the opportunity to provide you insight into an activity which had been put together by a large range of experts around this topic, which is on the heat stored in the Earth system between 1960 and 2020, with the question asking, where does the energy go? So as just mentioned before, this is a synthesis which is based on a contribution of many experts in expertise on the so-called Earth heat inventory. And we have started launched this work with the first publication in 2020, providing insight on the Earth heat inventory up to 2018. And we have updated and extended this analysis with a recent publication, which I will provide you here in this presentation. So the Earth's energy balance is one of the most fundamental conditions for making planet Earth conducive to sustaining life. And currently, due to the emissions of greenhouse gases, the Earth is out of energy balance. And so this causes an accumulation of additional heating in the climate system, driven by a positive Earth energy imbalance, where less energy is leaving the system as compared to the incoming solar radiation. And this heat, which is accumulated in the Earth system, is stored in the different components of the Earth system, such as the ocean, the atmosphere, the land, and the cryosphere. And this in turn has consequences with continuous warming of the ocean, the land, the cryosphere, and the atmosphere. So why should we care about this aspect? So here is a schematic overview on the Earth heat inventory with its specific implications, as I just mentioned. So again, the accumulation of thermal energy in the Earth system is the root cause of the various facets of observed climate change. And this in turn leads to, again, the warming of the atmosphere, the land, the heat available to melt, the ice in the cryosphere, and to warm the ocean. And this in turn has various cascading aspects, like the increase in atmospheric temperatures or water vapor, changes in atmospheric circulation and atmospheric convection streams, weather extremes. Then also for the cryosphere aspects, the permafrost extends, the ice sheet melt, decrease in the Arctic sea ice, snow cover, and the decrease in glacier mass loss, and the ground ice volume. But also for the ocean, with the ocean warming, then the related sea level together with the melting of land-based ice, the extremes, increase in marine extremes, and then for the land, for example, for the flooding, increase in erosion, ground heat storage, ground subsidence, soil water, etc. increase. And this in turn have impacts on the ecosystems and on the human systems, synthesized here schematically as has been assessed in the Working Group 2 report of the IPCC R6. So this Earth heat inventory, which provides the accumulation of heat and hence with a rate of change in time, the Earth's value for the Earth's energy imbalance, provides a measure of the current status and the future perspective of planetary warming, because it determines how much and where the heat is stored and how this changes over time. And it's currently the best available estimate for the Earth energy imbalance absolute value. And we will hear more from the preceding talk on the ways forward in order to have best estimates for the temporal changes of the Earth energy imbalance. It provides an integrated view of effective relative climate forcing, the Earth's surface temperature response, and the climate sensitivity. And it informs us about the status and also on the perspective of global warming, leveraging the question of how much heat is in the pipeline. And it allows for assessing the status of the global climate observing system, its different components, because we address all of them, the atmosphere, the land, the ocean, and the cryosphere, and the provision of valuable recommendation for fit-for-purpose climate monitoring. And it enables concerted international innovative multidisciplinary collaboration, and hence posing new questions in terms of climate science. So what we have done is, as you could see in this second slide I've shown you with the various experts from the different institutions, with expertise on land warming, on ocean warming, on warming the heat available to melt the ice and the heat content in the atmosphere, different approaches which are available today in order to provide these estimates back to the 60s up to the year 2022. And so you can see here the different outcomes, but I will now further go into detail for each of the components. So I will start with what has been done in order to provide an estimate mostly from observation for the heat available to warm the land. So what has been used are borehole temperature profile measurements, and there is one publication which had been developed, or two, in parallel to these initiatives to provide more insights on this estimate. You can see in Cuesta Valero et al. In 2020 and 22, and providing here an updated evaluation from the borehole temperature profile measurements, which improved uncertainty evaluations, providing the global cumulative heat storage within continental land masses since the 60s, and including also the uncertainty level. And on the upper right panel, you can see the locations where the borehole temperatures had been available also as a function of time. Then, which had been new for this recent publication was the estimate of the heat available to warm, also to melt the permafrost and warm inland water. So to the estimate of inland water storage. Used here had been a combined, or let's say a so-called hybrid approach, where you use reanalysis systems and model results, which had been more discussed also in Nitzborn et al. 22, to provide an estimate on the permafrost heat storage. And also for the inland water storage, it's based on these simulations, which is also further detailed in Van der Kelen et al. In 2020, to provide through the 4 lake models and different global lake simulations, an estimate for the inland water heat storage. Then this is what has been coming out, and again, which had been synthesized in a parallel paper in Cuesta Valero in 23. On these 3 estimates put together for the ground, inland water, and permafrost. And on the right-hand side, you can see the different contributions leveraging the different roles for this part of the Earth heat inventory, with providing different values over the period, and that the ground stores is the major component for the estimate of the continental heat storage. The atmospheric heat content had been evaluated or drawn from a combined analysis of reanalysis systems, atmospheric reanalysis systems, and remote sensing data. And you can see here on the left-hand side the different anomaly trends from the 60s, but also through different periods, which are linked to the availability of the different data sets. And on the right-hand side, you can see a distinction between the different rate of changes of the atmospheric heat content, leveraging again, on the one hand side, the change over time and the increase over time, where we'll come back in this presentation, and we will hear also in the other 2 presentations a lot about this topic, and also with respect to the different regions, like for the global scale, but also regional scale, like a focus on the tropics or on the extratropical areas. And so this is for the atmospheric part. This is what has been estimated from the different experts and the heat available to melt the ice through a combined use of in situ and remote sensing observation, reanalysis data, and model data, assuming that the energy uptake by each of the component is directly proportional to its mass loss. And so you can see here that there had been obtained an estimate for the Greenland ice sheet, the glaciers, the Arctic sea ice, and Arctic ice sheet, also in collaboration with corresponding international initiatives like IMBI or GLIMBI, in order to which provide information on the mass loss, and which have been further analyzed in order to provide then the estimate for the heat available to melt the ice. Then for the ocean, we have updated the efforts which had been started in 2020, now with an increased inclusion of more data sets from different international in situ-based products, which are based on different products, but which had been all provided in a similar theme with the different area coverages between 60 degrees north and 60 degrees south, and excluding the 300-meter bathymetry, etc. And so what you can clearly see, these are the results here for the different depth layers obtained from the ensemble mean, and also the spread, which is provided here as an uncertainty indication, not a real uncertainty. And they show all a global increase in ocean warming over the period 71 to 22 as a specific rate of 0.4 watt per meter square. This is another similar to what you could see before on the atmosphere for the ocean surface with respect to leveraging the different rates of change of ocean warming in the different depth layers, where you can also clearly see that in all the depth layers have shown an increase in warming, and particularly you can see on the right-hand side, you have also the different rates of change over the longer term periods up to the most recent period, which shows between the intermediate depth layer showing, indicating also redistribution, an increased redistribution of heat into the deeper layers of the ocean. What you can also see, which is currently, I will not have time to go further leverage this, is that there's also an increased spread in the most recent products, and there's a specific activity also in WCRP and the GDAP, which are having a specific focus on, amongst others, on this specific topic. So we have then used this information for land, ocean, atmosphere, and cryosphere in order to provide then a figure on how much and where the heat is accumulated in the Earth system, which you can see here with a heat gain of 381 zetajoules during the period of 71 to 2020. And with the redistribution of where the heat is going, with about 90% for the ocean, then the second order by land, and then following by the cryosphere, and then by the atmosphere. And then, as mentioned before, by taking out the rate of change, we have obtained a value, an absolute value for the Earth energy imbalance from 71 on long-term abstract up to 2020 of about 0.5 watt per meter square, and which has significantly increased during the most recent period, 2005 to 2020. So I would like specifically have a word, and also I think in the light of the following presentations with respect on the changes of the Earth energy imbalance we have observed. So both cycles of the Earth heat inventory evaluation have shown that the Earth energy imbalance increased over the most recent decade. And so we have seen this in this recent publication, but we have also already reported this in the publication in 2020. Then concurrently, there had been publications using other independent estimates, such as, for example, an estimate from remote sensing on the ocean heat content through the sea level budget approach, which provide a similar result, and also the work which will be presented in the following presentation by Norman Loeb on more details. So I didn't add this here because you will have it later. And so here, this is another representation from a paper which is currently under review, which again puts a vision in terms of how the different components in the Earth system have changed over time. And also the message here is what we can see for the moment is that for the most recent period, we have an increase over time for all the Earth system components with respect to the accumulation of heat in the Earth system. So it's just a slide to introduce the upcoming presentations, and so it's a slide that this is a discussion which is of a matter of an emergency, also to understand why there is an increased rate of change in the accumulation of heat in the Earth system, which is very high. And there are different discussions about this, such as we will hear in detail, so I will not go in too much. In the discussion linked to the reflection of energy back into space by clouds and sea ice and increased well-mixed greenhouse gases and vapor vapor. Then there was a study from Kramer et al. In 21 with the all-sky instantaneous relative forcing, showing a similar increase from that independent estimates and accounting for these positive trends through a combination of rising concentration of greenhouse gases and recent reductions in aerosol emissions. And then for the third talk we will have today with also a discussion on this increase with the climate models that show that such a trend is unlikely to be explained by internal variability. So there is still discussion on the origin and what is happening. So there are different other theorems, and I think it would be very nice to have a common discussion today with you here as the experts on these outcomes, and an exciting step forwards to understand what is happening. So one aspect which I didn't have time is that the study
5 minutes.
provided, yes? Provided a lot of insights in terms of the observing system recommendations. So I did not present them all here, and but it's an important aspect and a new opportunity also to highlight the gaps in the observing system. So this is just a summary. I think I'm running out of time to provide again a synthesis on the value obtained, and to highlight again that the Earth heat inventory is one of the most fundamental global climate indicators, and that this community calls for an implementation of the Earth heat inventory indicator into the Paris Agreement global stock taste based on best available science. And again, with this effort that as a general recommendation, which we have many details accumulated together on archiving, rescuing, continuing extension and calibration efforts for the global climate observing system. Thank you very much.
Thank you, Karina, for your presentation. And just a reminder that if anyone has questions for Karina, please use the Q&A box, and question will be addressed at the end of the study presentation. And now it's my pleasure to introduce our second speaker, Dr. Norman Loeb. Norman is NASA Senior Scientist for Radiation Sciences and Principal Investigator of the Clouds and the Earth's Radiant Energy System service. He is a member of the Climate Science Branch at NASA Langley Center Research and serves as a commissioner for the International Radiation Commission. He is co-leader of the Earth Radiation Budget Working Group. Dr. Loeb has authored over 180 publications and 6 book chapters, and has received numerous awards, including NASA's Distinguished Service Medal and RAID Award. He is a fellow of the American Meteorological Society and member of the American Geophysical Union. Okay, now, Norman, we are ready to start with your webinar. The floor is yours. Thank you.
Okay, thank you. Can you see the slides?
Yes.
Okay, great. All right, I'm going to talk more about what's happened this century. So this is a sort of picture you see in a first class of Climate 101, and I'm just showing it just to put the numbers in context. The green here is the energy imbalance. In this case, it's an estimate from 2005 to 2015, so it's a 10-year average based on in situ, the kinds of measurements Karina was talking about, in addition to other parts of storage in the system. It's essentially a balance between very large numbers. The incoming solar radiation is 340 watts, about 100 watts are reflected, and emission is about 240 watts. So 0.7 versus things like 240. Measuring this is from satellite is extremely difficult to get in terms of an absolute sense. So what we do in the satellite world is we anchor the values to the in situ, but it's a sort of one-time adjustment. You basically take this 10-year period and you adjust the shortwave and long wave within uncertainty so that the absolute value of the net agrees with the in situ value. But the variability is entirely independent. It's from the satellite itself. Satellites have been used a long time for Earth radiation budget. Following Sputnik in '57, NASA Explorer 6 was launched in '59, and then later that year, Explorer 7 was launched with a set of detectors for measuring Earth radiation. And so the thought was really Earth radiation and weather are really tightly linked. And so they wanted to measure radiation to better understand weather. And here's an announcement in the New York Times from 1959 talking about the incredible new launch of a first satellite for measuring weather. Vern Sumi was the first instrument the provider, and here he is with his spherical balls, and so that's from the Explorer 7. So that's where we started. We've really, this has been done a lot, and I'm not going to go through the whole history, but the history is actually very fascinating of all of the instruments. So fast forward to today, Ceres, which is the clouds in the Earth's radiant energy system. Essentially, these are broadband measurements. So we're measuring in the short wave, 0.3 to 5 microns, total channel, 0.3 to 200 microns, and then we have a window channel on 5 of our instruments. And then the 6th model uses a long wave instead of a window. So we've flown on the TRIM satellite, the Terra, Aqua, SUMI MPP, and NOAA 20. The spatial resolution of these are depends on the orbit altitude, 10 kilometers for TRIM, 20 for Terra, Aqua, and 24 for MPP and NOAA 20. And these instruments are very advanced. They can do all kinds of different scan modes. They can go in a cross-track mode. You can program them to rotate in azimuth as they scan in elevation, or you can even optimize the number of samples over a field campaign or use them to intercalibrate with other instruments. And they also fly alongside sophisticated imagers like MODIS and VIIRS. And so we exploit that synergy in the Ceres project to produce our data products. And so here's the flight schedule. So TRIM, we had a failure, then so it didn't last. This was just over the tropics. That was the proto-flight model. We were able to fix things so that things worked better for the actual flight models. And so Terra launched in 1999, was a 5-year mission, and 23 years on, it's still operating. We have 2 instruments there. We expect that could go until 2026. Aqua, launched in 2002, is going strong, which is really quite remarkable when you think about it. All of the instruments and the satellite have been working for all of this time. It's an engineering marvel in my mind. We did have a problem with the FM4 shortwave channel, but the FM3 is working fine. SUMI MPP FM5 was launched in 2011, and that's doing fine. We're not sure how long that's going to keep going. We're hoping it continues. We're concerned about that. And we're trying to convince the people that make those decisions to keep it flying as long as we can to avoid a risk of a data gap in the record. And FM6 was launched in 2017 and is working fine. The follow-on to Ceres is an instrument called Libra, which is scheduled to launch in 2027, which isn't that far away. And another concern we have is that there is no plan for another one at this point. That's it. I hope that changes, and I'm trying to do everything I can to, again, convince the people that make those decisions that this is a critical measurement that needs to continue. In addition to Ceres, I mentioned we use the imagers, MODIS and VIIRS. We also use the geostationary imagers as well, because what we want to get is complete sampling of the diurnal cycle at hourly resolution. We also bring in reanalysis from GMAO and aerosol assimilation as well, snow and ice maps, solar irradiance, et cetera. It's just a number of different inputs. And these are all kind of integrated together and intercalibrated to make sure that we can get the best quality measurements from the entire suite. So just a bit of eye candy. This is what the net flux looks like regionally at hourly. The blue and purple is nighttime, and the red, green, orange, and yellow is daytime. If there were no clouds, you'd have a nice bullseye, but the clouds clearly are distorting things, and really this gives you an appreciation of the atmosphere as a fluid, and clouds being very difficult. And so it's no reason why clouds are a major source of uncertainty in projecting how the system will warm in response to doubling CO2. This is the global mean all-sky TOA fluxes. So the net is essentially Earth's energy imbalance. When you average it globally, it's what we refer to as EEI. And the components making up that is the absorbed solar radiation and the outgoing radiation. So these are anomalies relative to climatology. And the convention here, anything here that's an anomaly that's positive is energy added to the system, negative is energy removed from the system. And so the thing that strikes you is there's a lot of internal variability at the monthly in these thin lines, and the thicker lines are the 12-month running average. And you also have La Niñas and El Niños that are shaded in gray here in terms of the multivariate ENSO index. But superimposed on this variability is a long-term trend, especially in ASR. And so here's the numbers. ASR trend is 0.73 watts per square meter per decade. OLR compensates slightly to give you about a half a watt per square meter per decade increase in net. So to put that in context, solar irradiance really between the first 10 years and the most recent 10 years up to February 2023, it means there's really no difference in terms of solar irradiance, but the absorbed solar radiation is 1 more watt in the last decade compared to the first decade of series. OLR increased 0.4, and so here's your doubling. So we have a doubling of Earth's energy imbalance since 2000, which is really quite scary. There we go. These are the regional patterns. Absorbed solar going a long way of the net, and I'm also showing the SST, and you can see, you've heard of these marine heat waves. Well, they're in the SST, and you see they're also in terms of the absorbed solar radiation. In fact, many of the hotspots in absorbed solar radiation and outgoing radiation seem to be very closely linked to the pattern in SST. You've got the cooling off of South America and the stratocumulus regions. You've got reductions, more reflection, and the opposite off of North America. You got warming and then a reduction in cloud and an increase in absorbed solar radiation. The net isn't so clean. It's not so nicely correlated with SST, except in the low cloud areas, because those are dominated by the reflected solar. So these patterns, I think, are really interesting to tell you what's the dominant driver, at least for ASR and OLR, but not necessarily net. And I'll come back to that. How confident are we in these? Well, we have all of these series instruments on different platforms, launched in different times. So if we have a common period, which was kind of brief because we were operating some of these in wrap mode, which doesn't do well for sort of global means. So what we have is a common climatology over a short period, and we could look at the anomalies from these different satellites, and they track each other really well. They're at the monthly level, they're down to a few tenths of a watt per square meter, 1 sigma, and there's no drift of one relative to the other. If we take the 2 longest records, Terra and Aqua, and compare those directly at the global level, the left here is just showing Terra alone, looking at the trend in the net as a function of record length, and you can see the variability, the uncertainty. You get out of the uncertainty once you get a long enough record of about 13 years, and it's been pretty solid ever since. If you look at Terra minus Aqua anomalies and you do the same thing, you see that they're consistent down to about a tenth of a watt per square meter per decade, which is really quite phenomenal for these types of instruments built in the 1990s. So what we can do, as Karina mentioned, this extra energy entering the system, most of it ends up as heat storage in the ocean. And so this beautiful network of Argo floats, which sample down to 2,000 meters, can give you, they give you temperature salinity from which you can get the ocean heat content, and the tendency of that gives you the ocean heating rate. And since most of this excess energy goes here in the ocean, well, the TOA results and the ocean heating rate should be consistent in terms of their variability. And so this is what we find when you compare them. So the net TOA in red from series, and then this is the planetary heat uptake from in situ. Again, this is using the Argo floats together with the other sources of storage in the system, but it's really dominated by the ocean. So the variability is pretty consistent. These are annual averages 6 months apart. But what's striking is the trend from series and the in situ are consistent, again, to better than 1/10 of a watt per square meter, just as I showed when I compared the Terra and Aqua records. This period is from 2005, so this is just the Argo period. So we're getting consistent results, and this is updated since our paper in 2021. We added a few more years, and things are actually looking even better as we add more data. So I think there's multiple lines of evidence that this is a pretty robust result. It's pretty alarming. We can do an attribution from an observational perspective. You do what's called a radiative perturbation analysis, where you look at a variable, let's say water vapor. You hold everything constant at climatology in one calculation, and then you do the same with every variable but water vapor and take the difference to see the impact of just water vapor changes on the TOA radiation. So we did this for a number of variables, and what we found is this big signal in ASR is primarily due to cloud changes, as well as surface albedo changes, which is primarily associated with snow and ice. Aerosols here, we only really do the direct effect because these are observations. You need it's easier to do with a model to look at the indirect effect, because you can't hold things, aerosols constant in observations. Everything is varying. So the direct effect is very small, but there could be an indirect effect that's really contributing to the cloud contribution here. Water vapor and other, this is greenhouse gases. They're positive. Temperature is negative because you're increasing temperature, so that means more emission to space. But overall, the temperature is really overwhelmed by all of these different contributions to give you this positive total. So clouds are a big driver, as well as water vapor, surface, greenhouse gases. They're all playing a role. This puts into context the, if you take the Earth Energy Imbalance and you calculate the planetary heat content by integrating over the whole globe.
Norman, 5 minutes left.
And then taking a cumulative sort of energy over the series period, you could see a very clear trend, as opposed to surface temperature, which is much more variable. Not too surprising. It's a point at the air-sea interface, air-atmosphere interface. So it's impacted by much more things. This is the integral over the whole climate system. So arguably, it's a much more fundamental measurement of climate than what we typically think about in terms of surface air temperature. To put it in context, 0.7 watts, I mentioned earlier, is small, but the accumulation of energy is pretty large. It's 344 terawatts, which is 60 times greater than the global energy production. So it's not that small, really. So what's going on, and Priyam will probably talk a little bit more about this, and I'll just briefly talk about it. So the forcings on the system, if you look at the system as a forcing response paradigm, forcing, you can have solar radiation changes, and I showed that that was negligible. Increases in greenhouse gases and decreases in aerosols, these are important. And then feedbacks as well from clouds, water vapor, surface albedo. But when you're looking at a few decades, there's also internal variability in the system that can fool you. And so one of the things I did, which I think I'm puzzling over still, which is kind of a fun result, I looked at the series period and I divided it into these different sub-periods, the hiatus, the transition to El Nino period. So the El Nino here being the 2015-2016 El Nino, and then post El Nino from basically 2016 to 2022, and then the full period. And I broke out each component in terms of trend, in terms of the solar irradiance, just the solar part, ASR, OLR, and net. And what you find is when you look at the hiatus, you look at the red and the blue, they're relatively small, but then they really get large for the El Nino transition to El Nino period. So the red goes from near 0 to 1.5, and the blue goes down. and then they come back down after the El Nino. But what's striking to me is the net. The net is nearly constant across these different periods. Despite all of that internal variability, it's basically constant to better than 1/10 of a watt per square meter, which is amazing. So it implies that the rate of increase in planetary heat uptake is relatively insensitive to internal climate variability at these timescales that I'm looking at. So it also supports the idea that the relative contribution of anthropogenic radiative forcing to net trends is much larger than the radiative response. And I think this is something that Ryan Kramer was also showing as well. So this is just another way of illustrating that. The other thing briefly I'll talk about, it's a new activity that I'm very excited about because we've had this wonderful set of observations out to present, yet our climate models that we want to compare against stop in 2014 for CMIP6. And so a lot of variability I mentioned happened after 2014, and this is a list of some of the things. And many of the model inputs have been updated substantially since CMIP6. So Gavin, recognizing this, is leading a new relatively low-cost model into comparison. He calls it series MIP. And the focus is going to be the series period with updated forcings and the most recent SST and emissions covering 1990 to 2021. He's starting in 1990 to allow 10 years of spin up. The diagnostic focus is going to be Earth Energy Imbalance and atmospheric feedbacks, and it's also going to be looking at the COSP simulator, so you can look at clouds as well. And he's trying to get the various modeling centers that have contributed to CMIP6 to participate in this. And I think it's really important because the AMIP simulations are probably the most appropriate simulations to use to compare with these observations. And it's not just series that we have, we also have Calypso CloudSat that have been taking incredible measurements. So it's amazing that this hasn't been done yet, but you know, better late than never, and hopefully we'll be updating more frequently in the future. So we have an AGU fall session on this. So I encourage you, if you're interested in this topic, to attend, and even better, submit an abstract. So in conclusion, the current satellites seem to be pretty robust in terms of detecting this. The comparisons are showing they're about a 1/10 of a watt per square meter per decade ability to track EEI. Multiple lines of evidence are showing that EEI has doubled since 2000. And there's various changes in the climate system from clouds, sea ice, water vapor, trace gases that are responsible. And then this interesting puzzle of mine about the internal variability in the system seems to be pretty critical for ASR and OLR, but net is very stubbornly constant across all of these different events, a hiatus and transition to El Nino and post El Nino, which supports this idea that really that one is probably primarily driven by anthropogenic forcing and not so much the internal variability. And I think Priyam is going to show that actually in his talk. So that's all I have. Thank you.
Thanks, Norman. Thank you. It's really nice talk. As before, if anyone has questions for Norman, so please post them in the Q&A box, and we will address them during the discussion session following the next speaker. So now it's now my pleasure to introduce Dr. Shivram Rahman. Thank you. Sorry if pronunciation is not good. Prem is an advanced student program ASP postdoc fellow at the NCAR, and he completed his PhD in atmospheric and oceanic sciences in 2021 at Princeton University. And he is interested in radiative transfer, radiative forcing and feedbacks, climate variabilities, and satellite observations of Earth's radiation and budget and clouds. So prior to his PhD, he received a bachelor degree in the mathematics and a minor in physics in 2016 from the University of Minnesota, Twin Cities. So Priyam, the floor is yours. Please correct me your name. Sorry.
No, that's fine. Yeah, Lijing. Yeah, my name is Shiv Priyam Raghuraman. Yeah, I go mostly by Priyam. Yeah, thanks to the organizers, Lijing, Annalisa, Marcus, Nico for inviting me. And thanks to Norman and Karina for giving very nice talks that I'll definitely build on now. So I'll be talking about EEI especially through its visible and infrared components, the solar radiation reflected from Earth on the left, as well as the infrared radiation emitted from the planet, using satellite measurements, series that Norman talked about, and importantly, climate model experiments, which can help explain recent changes in the EEI. So as we've seen, there's this satellite observed trend in EEI that we have. Here I show the intra-annual anomalies in the globally averaged net radiative imbalance. So that's what we call EEI. And most results are going to be global unless I say otherwise. You can see ups and downs in the time series, but overall there's this 0.38 watts per meter square per decade trend from 2001 to 2020. And this, for reference, again, like Karina showed, the mean EEI over this period is almost a watt per meter square. So 0.38 watts per meter square per decade is quite substantial. And as we saw, EEI is mostly an ocean heating rate. And so a trend in EEI, a positive trend, is an acceleration in ocean heat content. So there's a lot of ocean heat accumulating quickly. And as we've seen, there's a lot of observational evidence now to show this from different sources, from the deep ocean to geodetic satellite measurements to atmospheric measurements to actually in situ measurements too. So it's quite robust that this trend is occurring. And so the question is, why is this increasing? And a natural question, the null hypothesis would be, is it just due to internal variability? And models can then help us understand this observed climate data record. And a second question we'll have is, how is this increase manifesting across the infrared and solar spectra? So briefly, the methodology I'll use would be we have observations from series of the net radiative imbalance, temporal anomalies and trends on the left-hand side of this equation. And on the right, we have the total EEI as well coming from climate models. So you can get this from CMIP6 historical runs. We did an extra set of AMIP simulations all the way to 2020. 20 realizations of prescribed SSTs and sea ice and forcing. That's the AM4 PSST plus ERF. And then we basically have almost 6 models and over 150 realizations. Now, how we can break this down, which is easier in the model world, is the forcing feedback framework, where we have an external perturbation to the climate system, this effective radiative forcing. So this can be a brighter sun, more greenhouse gases, aerosol changes. And in response, the Earth tries to stabilize again and has this radiative response, which is what we call lambda delta TS. Lambda is the climate feedback that can amplify or diminish the surface temperature anomaly. So how we separate the total into these components is we do an additional experiment in GFDL AM4. We prescribe the SSTs and sea ice, but we hold the forcing fixed. So we don't have any gases changing or anything else. And so that gives you just the response of the climate system to the forcing. And then the difference between the total and the response terms will give us the forcing over this period, the ERF. And finally, this is a 20-year period, as Norman has showed, that there are these wiggles and they could affect the trend that we see. Of course, there are interannual variations, but what we're looking into is how much is the trend itself impacted by internal changes. And so that we can get from almost 50 models in the CMIP6 archive, and I'll explain how we get that. And then we do additional simulations with just the atmosphere model. Overall, we're letting the model do its own thing in a pre-industrial setting, pre-human influence, and try to see what's the range of trends we could get. And I'll re-explain these experiments as and when they pop up. So first on the right-hand side, I plot the so the EEI global anomalies in the GFDL's coupled model simulation, a control simulation over 600 years. And what we do is just slice the simulation into 20-year periods, consecutive, non-overlapping, and see what's the trend in each of these periods. And those trends are then plotted as gray circles on the left. And so you can see is that sometimes there is a positive trend, sometimes there's a negative trend, but overall, over a long multi-centennial scale, there's basically averaging around plus or minus 0.19 watts per meter squared per decade. And we also do some atmosphere-only simulations, and it shows a similar range, suggesting that most of the noise we get in the system and even a trend sense is from the atmosphere. And importantly, then we show on the black cross is series, that 0.38 watts per meter squared per decade I showed, with some observational uncertainty, pretty conservative estimate. And what we see is that the series lies above the range of these gray circles, which is what we call epsilon, implying that internal variability alone can't explain this trend. And you'll see a couple of realizations do stray into the observational range, but we'll deal with that quantitatively in a minute. But what about all the models I just spoke about? I plot the +2 sigma value here that you can get due to internal variability. These are these black bars on the right. And we see that this maximum trend that you could get from internal variability across models, across boundary conditions, across forcing is robust. They're all less than 0.2 watts per meter squared per decade that you could get from internal variations in the system. Series, this black line across with its observational uncertainty in gray, lies above all of them. And this tiny overlap that you do see between the upper end of trends that you could get from noise in the system and the lower end of the observed trend range in the gray due to potential satellite drift error or other observational uncertainties we deal with next. So this is a probability distribution where the gray is the full range of trends you can get from internal variability, and it produces a nice Gaussian distribution. The black is the observations, and we assume a Gaussian distribution of observational uncertainty here. We tried other distributions. The results are pretty insensitive. As you can see, the curves are very distinct, and it's exceedingly rare for internal variability to give us the observed trend. The high trends that you can get from internal variability get exceedingly improbable as we move to the right end of the gray distribution. And the low trends you can get from observational error is exceedingly improbable as we move to the left end of the observational distribution in the black. And since these are independent distributions, a random ENSO event shouldn't impact a satellite's movement. We can just multiply those two probabilities. And so we found that there's less than a 1% chance that you could, in the same 2-decade period, get a high trend from internal variability and have a biased low trend from observational error. So what then does produce this observed trend? So in GFDL-AM4, like I mentioned, only by including anthropogenic, meaning human-caused, forcing changes and the associated response, that's in the orange here, do we get this imbalance increase where the orange line now matches the series trend much better. And I'll discuss in a couple of slides why the response alone produces negative trends, which is more energy lost to space. And again, we simulated 20 realizations over this period for both experiments, so it's as apples to apples as we can get with the model. So here on the right inset, I show more clearly that the observations lay outside of those gray control simulations from the model. And in the orange, when human influence is included, only then does it start to overlap with observations. So this independently, we see also with other modeling centers that multiple CNIP6 large ensembles also agree with observations when anthropogenic forcing and response is included. The gray is just the control, and the green is when you have the anthropogenic forcing and response. Importantly, the first 5 models here are coupled models, and the final one is AM4 with the AMIP simulations. whether it's coupled or AMIP, we do see that the models are getting the increase in EEI and suggesting they at least have the right forcing and feedback physics overall. So what exactly caused this forcing increase? As Norman alluded to, there's been about a half, and Ryan Kramer's work, there's been about a half a watt per meter square per decade in forcing over this period in EEI. And we do further experiments and find that about 80% of this forcing is coming from greenhouse gas increases, and the rest is coming from aerosol decreases. And the sun, which would be natural changes, it doesn't really have a significant impact on the EEI. For reference, we've put in about a watt per meter square, so that's 0.49 watts per meter square per decades times 2 decades over the last 20 years. And this is from the IPCC AR6. We've put in about 2.7 watts per meter square over the last 250 years. And so we've basically put in about a third of the forcing of 250 years just in the last 20 years. So these are very rapid changes. And in some ways, we should be expecting to see changes in our EEI from observations. So now I was only showing a net radiative imbalance. What about its constituents? So EEI is the solar incoming S0 minus the outgoing radiation from the Earth. So that's reflected shortwave radiation, RSW, and the outgoing long-wave radiation, OLR. So I'll speak first about the reflected shortwave radiation and how its forcing and feedbacks manifest. So first, we find a massive decrease in reflection, globally average. This is the time series, the same black is series, then the red is forcing and feedbacks, and blue is just the feedbacks. So with just the feedbacks in the blue, what we see is that it gives a slight decrease in reflection over this period, but not as close as observations. But when forcing is then included in the simulations in the orange, we then get a trend line that tilts much more towards observations. So why is this happening? So a lot of it's to do with this forcing. GFDL's model shows a decrease in reflected sunlight from anthropogenic forcing, about minus 0.28 watts per meter square per decade. Sorry, for the reflected shortwave and OLR, negative means heating. This minus 0.28 is almost 40% of the total observed trend. And so it's worth breaking this forcing further into clear sky and cloud radiative effects. So on the right plot here, I show the shortwave cloud radiative effect, trends from all forcing agents in just the forcing alone. And we can see that many models, almost all models, show that the forcing-induced decrease in reflection in sunlight comes mainly from this cloud radiative effect from the shortwave CRE. And the bottom, we can further then break down this all forcing into greenhouse gases and aerosols, which I'll now explain mostly the aerosols in the next plot here. So on the right, we have the northern exotropics average trend. So in the black cross is again series, lies outside of the gray control simulations in the model. And in the blue, we have a decrease in reflected sunlight just from feedbacks in the system, the response, but it still doesn't line up with observations. But when we include forcing changes, then it does nicely align with the observations. The orange aligns with the black. So what's in the exotropics? Well, we have had in the last 20 years clean air laws in the US, Europe, China that decreased aerosol emissions. And so these decreased these light reflecting particles. So that would be this aerosol direct effect that does complement the cloud changes that I showed earlier. We also see an aerosol indirect effect where MODIS observations of liquid water path decreased in these latitudes. And AM4, the model, could only get this decrease in liquid water path when aerosol changes were included. And so the aerosol forcing contributions are very important in this period, but also I want to mention, and I won't go into too much detail, the greenhouse gas increases also cause these rapid cloud adjustments that decrease the cloud cover and reduce reflection, but you can ask me further in the questions about it. So overall, we find a massive decrease in reflection in the shortwave reflected. The forcing dominates this reduction from aerosol decreases and greenhouse gas increases, and clouds are mostly to blame. But finally, in response to this forcing, temperatures rise, sea ice melts. And so at the far right of the right plot, we show the polar change in reflected sunlight. This is area average. So all of these regions add up to the globe. And so what we see is that sea ice reduction reduces reflection because ice is bright and white, so it reflects sunlight, and when it decreases, that reflection also decreases. And so you see the decrease in reflection in the model as well as the observations. So finally, we also look at the other piece of the outgoing radiation, in the infrared wavelengths. So OLR, outgoing long wave radiation now. What we find is a slight increase in OLR globally. If you look at just the blue, which is just the response and feedbacks in the system, that causes a very positive trend more than the observations. But when you include forcing, that is greenhouse gas changes, etc., this then flattens the slope or trend, it brings it down. So why is that happening? First, the forcing, when greenhouse gases increase in the model, it reduces the outgoing longer radiation. So that's where this minus 0.26 and minus 0.27 watts per meter squared per decade come from. This is just showing that in the bottom that all the forcing in the long wave is predominantly greenhouse gas related. So this is this classical greenhouse effect where we have an increase in greenhouse gases, we should trap more infrared radiation. But in response to the CO2, methane, and other well-mixed greenhouse gases increasing, the planet warms over this period. So there's increased emission from this hotter planet, so a larger Planck response, as well as long-wave cloud feedbacks that are also diminishing this temperature response. And so what you can see on the right plot is that without any forcing changes in the blue, the planet is emitting a lot of infrared heat away to space. But when we add in the forcing changes in the orange, so greenhouse gas is increasing, it traps the long wave. And so here in the long wave, essentially, the feedbacks end up beating the forcing, whereas in the short wave, the feedbacks and forcing acted together to produce a very negative trend. So forcing reduces the emission from greenhouse gas increases, and feedbacks increase emission from a warmer planet and larger Planck response. And this feedbacks ends up beating the forcing. So as a summary, the observed increase in EEI that we see, it's exceptionally unlikely that this observed trend can be explained by internal variability alone. Anthropogenic forcing and feedbacks instead yield this observed trend in EEI. This manifests as a strongly negative shortwave trend where forcing and feedbacks are additive and slightly compensated by a slightly positive long-wave trend where forcing and feedbacks nearly cancel. And so a more broader conclusion is that these observed increases that we see in EEI doesn't come from the long-wave changes, but instead comes from shortwave reflection decreasing. So we always think increasing greenhouse gases means trapping more infrared heat. The classical greenhouse effect becomes larger. That's right, but the flip side is that the resulting warmer planet also now radiates more infrared heat to space. So the greenhouse gas heating impact is canceled. So instead, much of the imbalance then comes from the fact that we're receiving the same amount of sunlight, but reflecting back less, so a darker Earth. And because increased greenhouse gases cause cloud cover changes, less aerosols in the air to reflect light, sea ice decreases, these all end up causing this negative shortwave trend. So put simply, in response to external forcing in long wave and shortwave radiation, Earth has a stabilizing feedback only in the long wave and not in the short wave. So the planet accumulates heat in the short wave. That's it. Thank you.
Thank you, Priam, for your talk. And thank you all for this presentation. And I think that they all together gave a very nice overview of this topic. So we can go to the Q&A session and start looking at questions that are posted in the Q&A box. There were a few for Karina. She already started to answer. But eventually, if you want, Karina, in the first one that was asking more about the process of the borehole and I mean some on the methodology, if you eventually want to say a few words about that, maybe you can say more. The question about the process, the borehole, how to get a global value, and the methodology that you mentioned that are in the papers.
Yes, thank you. I have mentioned the specific papers, which has, as I said before, worked together in order to provide an in-depth discussion on the methodology, on how the different borehole estimates have been used through a so-called bootstrapped approach. And so they are very inhomogeneous, of course. So, and that's why you can also see in the time series that there are very large uncertainty bars. And so this is particularly with respect to the scarce data sampling. And another issue is also in terms of the observing system recommendations that after 2000, the data density also really hardly decreased. And also there is no globally organized data cartography for this type of data. So it's also all research program driven. And so these are the major outcomes in terms of the recommendation for these methodologies. But in terms of the technical question, I prefer to refer to the papers mentioned as we have worked with this expert.
Okay, thank you, Karina. I saw a question in the QA box to Prem. What do you make of the fact that none of the simulations produce EEI trend near the series mean? So can you answer this? Or?
Yeah, no, I was just typing the answer also, but great question, Robert. So I've looked deeply into AM4's issues with this. The other models we'll find out more from series MIP. In AM4 particularly, some of it is odd due to just a prescription issue where the NSIDC data for sea ice is actually decreasing around the Antarctic, but AMIP actually shows an increase over the same period. And so it's not even model related that this issue occurs. But a lot of it is to do with the model's cloud fields, where Southern Ocean cloud cover, for example, is decreasing in the observations, but it's increasing in the model in AM4. So there's possibly these underestimation of shortwave cloud feedbacks that are occurring there.
Can I follow up?
Yep.
There's a study, it hasn't been published yet, but there's a study that is a follow-on to PREEM's that does use other models, and they show a much better agreement with series. And again, the series MIP is going to give a whole bunch of other results from many other climate models. So I think it's exciting that we will have a much broader set of climate model simulations to work with.
Okay, just to follow this question, Norman. So you told us that the series map is mainly atmospheric only simulations. So what is the background of this considerations? Why not use coupled models or Earth system models to do this? Any considerations on this?
So is the question why use AMIP instead of coupled for comparing series? It's primarily because the internal variability in the coupled, you don't expect it to be consistent with a 20-year period from series. It's just series is just one realization of many that can come out of a coupled. So if you specify the SST and sea ice boundary conditions, you're at least anchoring the internal variability to be consistent with the measurements.
Okay, there's a question in the QA box for Norman that if the variability in EEI is not answer related, what drivers the observed multi-year variability?
So you need you need to look at the time scale I'm looking at. If I'm looking at monthly time scale or annual time scale, there's clearly ENSO signals in the net. What I did is I took the series 20-year period and I subdivided it into 3 that are, this what we used to call the hiatus. There's this transition to El Nino where you see rapid changes in ASR and OLR. And then after the 2015-2016 El Nino onwards, those are the 3 periods. So you have to be very specific. I'm not saying that ENSO isn't important at short timescales, but over those 3 timescales, it seems like it wasn't driving the EEI, but it was a critical part of driving variability in SST, ASR, and OLR. That was my point. So ENSO is important, but you have to consider what timescale you're thinking about.
Okay, so the follow-up question is for Karina, actually. Following this question, for variability in the various components of the EEI, ocean, land, atmospheric, or cryosphere. So can you say any variabilities interannual or month-to-month related to ENSO or other variabilities?
Yeah, so I mean, that's not a straightforward question. So I would echo what Norman just said. So in terms of the Earth energy imbalance, there are different possibilities to induce changes at different timescales. So starting from interannual timescales related to ENSO, but also Pacific decadal oscillations or climate variability, but also going up to longer timescales and including such as, for example, the solar cycle, etc. These are all signatures which are not, let's say, driving a trend, but could induce variations in the Earth energy imbalance itself. So with reflect in terms of how to look at the variation then in the other components apart from the ocean, this is very difficult. So for example, at least for what we can obtain today from the observations. So for the atmospheric time series, this is possible to do this type of analysis. And of course, there is this ENSO imprint. But for example, for the land component, it's not, there's a very, let's say, rough resolution. We don't have the resolution from the observations. So the time series is really flat and we are not able from, let's say, from the current observing system status to extract information on any variations at decadal scale, at interannual scale, for example. And so hence there is no reply, for example, for this component to provide in terms of reactions to ENSO. But yes, so it's more coming back to the Earth energy imbalance, at least to what we can say today from an observing system side. So that might be different reply for the model community.
That's great. Thanks, Karina. Just follow up with this observation system question. For cryosphere, we have ice sheets melting heat and sea ice melting heat. But in most of the models, they don't have ice sheets simulations, right? They cannot have resolve ice sheets melting. So what do you think? Because now the ice sheet melting is accelerating. So what do you think is the impact of the cryosphere on the EEI, and what is the implications for models?
Question to Priyam, no?
Yes, both of you.
Yeah, I mean, that's right. There's a lot of parameterizations that happen for the ice sheet, especially over land and stuff. I think it's hard to say without like a spatial comparison, especially at those timescales. For example, in the Antarctic, the model was underestimating some of the decreases that we see, but in the Arctic, it doesn't. So I think it will depend on each location. Yeah.
But something which is very interesting, and also starting with the dialogue, and also what just Norman introduced on this initiative on the series MIP, and also having this discussion, we had some discussions in terms of using the estimates then provided from the observations, albeit we have, let's say, constraints for some in terms of resolution, in terms of large uncertainties, in terms also that we have to rely on assumptions, particularly for the cryosphere estimate, because observations are missing that we have only a hybrid approach for the many estimates because we do not have observations. We have to rely on using also models and reanalysis systems. But there is also an opportunity then to what Priyam just said in terms of the parameterization in order to see when we start to intercompare these new estimates, which had never been provided in the aspect of heat availability to melt, for example, because everything had been related before on the mass loss aspect, allows new opportunities in order to advance on opportunities for improving parameterization, for understanding model gaps on whether there can be improvements made, because we have this kind of validation intercomparison, and even it has been also started to be used for model constraint approaches in order to advance on this aspect. Of course, you cannot replace, let's say, some lacking, but you could advance in terms of understanding of improved parameterizations, understanding how you can improve some biases in the models, and work across these hands. So this is new data set, a new discussion, which will for sure lead to some new opportunities and new questions, right?
Yeah. So Norman, do you have anything to add? You are muted.
No, I have nothing to add.
There are a few more questions. Yeah, there are a few more questions in the chat for Norman. One from Jake agreed that the constant net in the different time periods that you showed is curious. Do you know if this is also holds at the hemispheric scale?
I haven't done that. Maybe I will after I get off this webinar. That's a good question. So, I mean, one of the curious things, and maybe this relates a little bit to the previous question and models, certainly the trend over the entire period across the northern hemisphere and southern hemisphere are nearly identical. They're really, really close. I don't know if I looked at these sub-periods, if that would still hold. But one thing I also know about the models, and not just the GFDL model, but a few other models that I looked at, they seem to do very well in terms of the northern hemisphere trend in EEI, but the southern hemisphere trend is near zero in the models. And again, series is not showing that. It's basically consistent across the two hemispheres, which I think is pretty interesting, and is a question that really needs to be better understood, and maybe some of the reasons Priyam talked about here and in his paper about the Southern Ocean clouds and sea ice off of Antarctica in the model, and how that's represented. Maybe that's what's going on. But yeah, you know, as we get more of these climate model simulations over the whole period, there's going to be a lot of riddles like this that are going to come up, and I think we'll learn a lot.
And there is another question from Antonietta for Norman. Can we think of the effect of internal variability as just a redistribution of heat rather than affecting the net values over decadal periods?
Yeah, I think you can. I mean, when you think about the feedback response framework, you don't resolve all of that in that framework. You're just looking at the global, and you're just saying globally the system is forced and globally the system responds. Which of those two is dominating? But certainly under the hood, when you look at regionally, there's clearly redistribution of heat, not just regionally, but obviously in the ocean as well, vertically. So yeah, absolutely.
Can I comment on this?
Sure.
Because it's another, there was some papers in 2014 when there had been a lot of papers on the hiatus, for example. There was this paper from England in 2014, for example, who described the process of large heat redistribution in the ocean, leading also to a surfacing of heat coming back into the interaction with the atmosphere, from this redistribution. And so he was kind of predicting in his paper that we would see now an accelerated warming aspect. So that's also then in question in terms of the redistribution. I mean, it's in contradiction, for example, of the results of BRM, but it's still a question in the air whether we see this kind of effect or if it's superposed on other effects so that things are coming together. That's something to look at, where we would like to look if there is a, let's say, an anomalous strong heat release, for example, in the Southern Ocean, which is taking place according to the paper, and whether a redistribution effect, so in relation to the question from Antonietta, could be also responsible, maybe in part, to the increase we observe today. Question, what's the Norman Priam?
Yeah, I just wanted to say one thing. Yeah, I guess it's like chicken and egg. I think the atmosphere forces the ocean, so ocean can respond to and redistribute the heat, but at decadal scales of 20 years or so, it's harder and harder to explain how it could be just like a random event that these 20 years has caused such a big EEI increase. It would have to be, it sounds unlikely, but I think there's the redistribution is possible over some years, and then, yeah, I'll let someone else talk now.
There are no, I don't see other questions in the chat while we wait. I have a question for the three of you. So thinking of the coming years and thinking that the observation will continue to develop, so we will have longer record of observation that will help us to understand better this energy imbalance trends, but we will also model development, so we will have new components, better represented processes, etc. From what side do you expect more? I mean, more advancement, more understanding between the evolution, the improvement of observation and the improvement of models?
All right, could I respond to Gottfried's question quickly? First?
Yes.
Yeah. No, that's actually you jumped in at the right time. That's what I was trying to say in response to what Karina was talking about. Yeah, definitely the ocean heat uptake efficiency itself could be changing over this period, because in the long term, we don't really worry about that in the climate model, but over such periods, I think that coefficient, I think we call it gamma in the literature, can be pushing more heat into the ocean. And some models may be good at pushing it more into the deep ocean, and some may not be. I think you're exactly right, yeah.
Can I start to reply to Annalisa? So for your question, I think the biggest promise, or let's say expectation I see, is an increased collaboration between the two communities, benefiting that both are about on track to improve, etc. And so I think that we're touching here a topic, which is a topic or an indicator, whatever, which has a global scale impact, various impact on all different Earth system components. So I think that all the communities need to work together to understand this. And I think what I'm hoping that we are capable one day to really understand when the time series, such an indicator, which is a very integrated indicator, is changing, that we are able to attribute this instantaneous and to understand where we stand and where we are going. So that's my big hope. And I think that can be only achieved through concerted and multidisciplinary efforts and collaborations. So.
Yeah, from the observation side, one thing I'm really excited about is we've gotten to a point, what I showed was a comparison with the top of atmosphere satellite and primarily the in situ from Argo in terms of that plot, looking at the trend in EEI. Michael Mayer recently has a really nice product from Era 5 looking at the atmospheric component. And he looked at something that Greg Johnson had done just from using the ocean analysis, their rainforest analysis, neural network analysis of the ocean data. And he compared that with Ceres. And then he added on top of that the atmospheric storage. at annual resolution, and an incredible improvement at that time scale when you add the atmosphere compared to series, which I thought was really cool. So, you know, we're not just looking at decadal time scales, we're trying to go to annual and maybe even monthly one day. But I think we need to resolve those shorter time scales from the observing system. Ceres is getting that. That's the strength of Ceres at the top of atmosphere. But I think you want to resolve shorter time scales in the atmosphere and ocean to get at the processes more. So I think in terms of the observations, that's an avenue for improvement in response to your question. But the caveat I'm concerned about right now is the continuation of the satellite record. I don't, right now, there is no plan to continue series-like measurements, period, which is pretty scary. And there's no money. So I hope that turns around.
Thanks. Thanks. There is one question in the QA box for Prem, I think. Have you read this? Any clues based on your quite detailed EEI diagnostic analysis on the associated topmost ocean layer heat changes or changes in the long-term heat transfer coefficient towards deep ocean? Can you answer this?
Yeah, I was referring to this earlier. Yeah, thanks for it was a good question. Great comment too. Yeah, I mean, in a perfect model world, EEI is just related to ERF and the response. You know, if you smash the model with 4x CO2 and over multi-millennia, but even then the ocean, deep ocean matters. So over a 20-year period, like you're mentioning, it even matters more. So in my framework, I think I'm using the epsilon kind of to encapsulate this gamma, the ocean heat uptake efficiency, and other kind of internal changes in the system. So it could be that some models are deficient there, or some models are underestimating, relating back to Robert's question, that maybe that could be an issue in the models that we haven't looked at. Yeah.
Okay, I think we got the final question from Rowan that what is the predictions for EEI for the next decade or two? Are you expecting it to continue increasing or stabilize? What do the model predictions show? How dependent on AA and other scenario? For all of you.
I think I might try to say I think it's going to increase. The aerosol emissions will continue to decrease. China has become even more aggressive in the aerosol reductions that they've had. It's going to clean up the skies even more. I think greenhouse gases will continue to increase in the coming decade. After 2030, there are some changes that will happen. So I won't say, for example, the US's Inflation Reduction Act starts to really by 2035 half the greenhouse gas emissions. So if that does happen, maybe greenhouse gases start to stabilize, then maybe EEI could start changing course. But I would say this decade it probably will keep increasing. Low confidence, but.
Yeah, I would agree. I mean, from what we've seen so far, and if the effective radio forcing is really overwhelming the response, then as Prem said, the two players, aerosol decreases and well-mixed greenhouse gas increases, those are basically going to determine the answer.
Yes, I mean, it's the answer. So it depends on the choices which will be taken, right? And for the moment, everything is increasing, and also as Priyam was saying, the aerosols are decreasing, so this might exacerbate the effect. So yeah, difficult to answer, right? This kind of question of projections, but look at the IPCC for the forcing components, what's predicted there for different pathways, and you have the reply because we have a direct link of the forcing and the response of the system to the EEI.
I guess model projections wise, the model projections do show an increase in EEI, but if with the different scenarios, SSP 245, SSP 585, but yeah, if that's answering the sub question, yeah.
Okay, so we are 1 minute to the end of the 90 minutes that were supposed to be used for this webinar. So we want to give a round of applause and thank our speakers today. So thank you, Brian, thank you, Karina, and thank you, Norman, for your talks and for answering the question. Thank you for all the persons that attended and that for the questions raised in the Q&A. Thank you, Li Jing. Thank you, Nico and the WMO for the organization and the logistic of this webinar. And see you at the next in around 2 months. Thank you.
Thank you. Thank you. See you. See
Thanks
you
so much.
around.
Thank you.
Bye.
Bye.
Bye.